I will give a brief introduction of Professor Wang. Professor Wang received a BS degree in 2002 and PhD degree in 2007 from Tsinghua University, Beijing. So he is currently an associate professor with the Department of Electronics Engineering in Tsinghua University in Beijing. So Professor Wang is very active in many professional activities. He has received the Best Paper Award in FPGA 2017 and ISPSI in 2012, and also the Best Poster Award in PARC 2012. And he is a recipient of IBM S10 Faculty Award in 2010. And he is also a volunteer member of many leading conferences in this area, including the DAC 8, ICCAT, SPTech, etc. And he is also an associate editor for the IEEE translation on CAD and guest editor for integration on the real-time journal and IEEE translation on large-scale computing systems. And Dr. Wang is also the recipient of the National Science Fund for Outstanding Youth Fund in 2016. And most importantly, he is also the co-founder of bitwidth Tech, now valued over $100 million. So congratulations. So let's welcome Dr. Wang.
Thank you so much for having me here to give this lecture. Actually, I'm going to talk about what we have done in the last about 3 or 4 years in the university, and what we have done in the last year, and to now in the company for deep learning on FPGA and what we are going to do for the chip. And also I will try to, if we have time, I will try to go through what we ongoing research on the deep learning on the ReRAM, which is emergent memory. So this is these are the 3 parts. So I will try to discuss in today's lecture. And the first one is efficient deep learning processing unit design, kind of survey of what we think is very important in the past few years, and why we try to follow the way we design the deep learning on the FPGA. So the topic will focus on deep learning. We just focus on deep learning here. So what is deep learning? I think go through back to last 2 days, you heard a lot about deep learning. So I will just quite quickly go through what is deep learning here. So it's a kind of cutting edge of artificial intelligence, boosting from about 2006, and Hinton had a science paper, and they know how to train a deep neural nets. They finally find a method to train the deep neural nets, so that the deep neural nets has spread to different forms, such as deep neural nets and recursive neural nets, and non-structured memory actually is also a recurrent neural nets, and the convolutional neural nets are widely used in today's different application domains. So here are some very old examples. This is for the actually in 2011. You can see that for the speech recognition, using the DA instead of GMM and HMM, they have about 10% of increase in the accuracy of the speech recognition. And also, Google has a very interesting application to use the LSTM to do the natural language processing. You try to fulfill your email automatically and put it on the web as what you want. When you don't want to write so many words, then you can fill in the words and reply it very briefly to your for your email. And what is the most influential competition back to the last, I think, maybe a few years, and this year this competition comes to an end of the 2017. This is the ImageNet. one of the most famous database of the millions of pictures and with markers, and they try to have this database, and then to try to do some competitions on this database, ranging from the recognition, detection, and I'm listing here the detection part. So this is called MAD here, and we can see that for non-CNN to CNN base, it has a great boost, and then increase year by year till now is about 73.2 of the MAP of the detection. What is the detection? Detection is trying to find the coordinates of your interested thing, such as you find a person in the picture. So you not only recognize this is a person, but you have to give a bounding box of the person, such as then you output the 4 coordinates, and this means you detect the person, have the bounding box, and then you give out the coordinates of the person. So the image feature extraction and classification is widely used using this kind of CNN method. So these are some very basic applications of these CNN and LSTM, long-short-term memory, and the convolutional neural nets. And we also have some downloaded videos from the web. So, okay. So this is from the NVidia. So I just try to contact them and get the video from their website. So this is a very interesting topic of the self-driving here. So apparently this is in US, right? Yeah. Yeah, you can do everything, right? Seems like. Yeah, I think so. So this is from the car's view. And you have multiple sensors around the car. So for each view, you need to recognize what is in this picture. So they also disengage autopilot. So they also include the video control, audio control, right? But this is in US, right? So I also got a test video from one of my colleagues who is now trying to do the company on Momentum. They just got the funding from Mercedes. So this is I think it's real, but the car cannot do the anaba, let's say. Yeah, yeah. And it's a kind of a Chinese version, yeah, in mainland China. And this is the night, and you can see that there are some cameras here, and also it is auto drive. So it has a very not that good feeling of the turning around, right? But it can really catch what are on the road. So I didn't show and they didn't give me the car's view of what they recognize from the car, but I just got this kind of clips from the my friend founding the Momentum. Momentum is also I think now is valued over 100 million US dollars. Yeah, it's kind of crazy in China about this kind of AI-related company, especially for self-driving. So this is also a big term. So these guys are more on the computer vision part, so they are not on the driving part. So they are trying to recruit the people who know more about controlling the car, and then to do a better control of the car. So that's why they get the funding from the automotive companies such as Weilai, which is the biggest electrical car company of startups, and also from the Mercedes. I think last month something. So what we are caring about, sorry, this is from the Chinese NVidia company show. I just want to show that the key things, what the car says, all comes from the NVIDIa's PX2. At least they are announcing that they are trying to put all the computing on this. So that is what I'm caring about. That is the energy efficiency. So when you took your iPhone out, then it's about 3 to 10 watts, at least 3 to 4 watts of the main chip of your iPhone, and they will provide 1 to 10 gigaops, giga operation per second. And this one, this PX2, they can offer about 24 teraops per second. So, and NVIDIA said that automatic driving need about 10 to 100 teraops per computation power. So you think about this one, they will have about 250 watts for this single board. So it's quite energy heavy. So this picture also takes from the auto driving. They put this big machine at the back of their cars, and it's, when they pass the cars, it's quite noisy because they're a big fan trying to keep it cool in the car and keep this machine runs very efficiently. So energy efficiency is quite important. You have to deliver a higher performance per watt from everything, especially for this kind of computation-centric tasks. So I also get some of the videos from the other application domains, such as Waston. This is one of the main areas. I think the strong AI will happen. You need to calculate a lot of things then to make the cloud or the data server more clever. Okay, so this is also one of the market that we are targeting. That is the from the drone view. This is from Daejeon, and you can see that you can track and so detect the inch COI and then try to find what it is and try to track it. So these are trying to be put on the drone about this big and this big, and the main board are about this big. And you need to keep it under 1 watt or something like that. So if we want to put actually last year we want to put a 3 watt board on this kind of drones, but we failed because it cannot be, it's too hot. It's too hot. You need to put a fan there. And if you need to put a fan there, then you need to increase the capacity of the whole volume of the drone. Then the designer said, no, we are trying to get a smaller one. So you cannot put a fan in this kind of drone. So if you want to put your computing power in this kind of small devices, especially for the customers, then you need to keep it under 1 watt or below. But 1 watt, you need to do everything, right? So this is also one of the company in China which is funded by Tsinghua Alumni. So basically they have very good face recognition capability on the algorithm part. So this is not real, right? It seems to be not real, right?
你的需求会被看到，你的生活会被改变。
No, actually no. The key thing is they can put the power of the face recognition to every device. So not only the camera, but the robots, and the house and the buildings. So they are trying to put it in the real estimate of the smart home. They enable the robots to see and to recognize people. And the surveillance, which is very important. We can see that we can get some bad guys, and also the smart transportation. So yeah, so this is also from that company. Because personally we are friends, but this is more like a US movie, right? But these are extracted from the real cases.
经值班民警进一步研判，确认身份符合，逃犯付某当天不熬某，诈骗案在逃。2016年，旷世天眼识别狱警，通过与在逃犯人数据库的快速比对，确认符合。通过视频接力，分析在逃人员郝某的行动轨迹，于20分钟内成功将其状李某。经查案在逃。2016年，旷世天眼识别狱警。 通过与在逃犯人数据库的快速比对，确认符合，实时抓捕。每1分钟都有机会3号、林克等人员被旷世天眼识别，行踪因此被警方掌握，并形成轨迹，为公安情报研判、合成作战提供强有力的支撑。
So actually, this is happening in China. So the Chinese government is collaborated with all these algorithm companies to trying to do the kind of surveillance, big surveillance system. We have a lot of cameras all over the road and buildings, and some of them are for the transportation, and some of for the surveillance or to see if there is any unusual cases is happening. So for these videos, previously we just tried to get the videos and save to a server. And then if something happened, then we try to look into this video frame by frame to see if there are somebody suspicious, right? So this is a traditional way. But for now, we are trying to get this kind of video stream and then to do the computation and to find if there are somebody suspicious online. But their company is trying to do the accuracy thing. That means you try to find the person accurately, but how to improve the efficiency of the speed is what we are going to do, right? So we can put the smart capability onto the camera or back to the server for multiple ways of the cameras. So this is what we are now doing in China. So my research topic is on the energy efficiency. So I just trying to emphasize. And there are 3 ways of to improve the energy efficiency. One is the scaling down. So sorry that I didn't put all the PPT previously too, but because I tried to add something into the whole slides and to make it more logical. So the first way is trying to do the scaling down. But scaling down is kind of stop, or the benefit from scaling down is not that big after 2005. And so after that, we are trying to look at to use the heterogeneous multi-core, or at least multi-core, and then heterogeneous for different applications, and to boost the energy efficiency of specific applications. And now, because these two ways are bounded by the 0 and 1 flip, because a CMOS gate or the inverter is a 0 to 1 or 1 to 0, so there are basic flaw of this energy consumption, even though you have a 1 nanometer transistor underneath, but you have this 0 to 1 or 1 to 0, the basic component of this dynamic power of these inverters. So if you want to break this barrier, then you may need to do a third way, maybe the emerging device and the emerging computing models for different applications. So what I'm talking about is more on this part, and on the deep learning and the emerging device, if I have some time. Yeah. So the research in my group is in two directions. One is the data-centric energy efficient computing systems that design XPU. So basically, I don't know what is the more important application, so I just trying to do a lot of things, such as machine learning, graph, big graph computing, and time series for the IoT, because each sensor you have a time and then you have a value, and from the time you see a time series, then for this time series what you can find. So there are a lot of time series algorithms and database. You need to store your data first and then you do the analysis. So database is the basic one, and these are the data analysis method. So all these things you may do a dedicated accelerator, or you try to design a framework or a processor for it. And the last but is a very important thing is that you may try to use a high-level synthesis, and you design the C code and then you use a high-level synthesis to transfer it into the hardware. So these all can use to boost the energy efficiency of the applications. But I'm more focused on the accelerator and the framework. I'm not a extra less guy. So what I'm talking about today is for machine learning or for the deep learning part, how to design the accelerator, and what we are trying to put it into a framework or put it into a processor way. That is, you try to get the basic components of the computation and try to extract them into instructions. Then you can try to make the description of the neural nets into different instruction series. So then you can do using one hardware for all the deep learning algorithms. And the other one is the neuromorphic system. We basically use CMOS plus emerging device to do the large scale and self-learning system. So this is a target, right? This is a target. So for this part, the learning scheme is very important. So far, I didn't find a very good learning scheme, not only from the deep learning part, but from the neuromorphic part. We didn't find a really interesting or useful learning schemes. But we tried to do some architecture in the EDA for the deep learning around the emerging device. And we tried to do some chips, also collaboration with the professors in Tsinghua University here. So what I have done in hardware computing research, including the embedded video analysis, data mining, and some platform work. Before I do the convolution neural net with Microsoft in 2013, actually I started this kind of using FPGA to do the acceleration back to 2007 and 2008, because at that time I was an intern in Microsoft Research Asia. So you can see that Microsoft, which is a software company, they put a lot of effort on the using the hardware or using the FPGA to do the computation. So that time I do the search, and then with the IBM to do the time series data mining hardware database. So these are on the server part, and these are on the embedded part, such as using the CV computer vision method to do the car detection, tracking, and 3D reconstruction. Actually, a lot of things are now moved to the CM part, but previously using computer vision, you can do quite good. And stereo vision and SLAM is also very interesting for now. It's also very interesting for robotics, because for robotic, you need to know where I am, and that is the SLAM. So you need to localize yourself. And the other one is you need to know how far I'm from another object. So that is the stereo vision. So you need to know the distance. And you need to know what are around. So you need to know, you're using the CNN to try to recognize what are around you. So these are, I think, three very important things or algorithms that you need to do when you're designing a robots. So robots is a very big concept from a very small one, such as a drone or even smaller, and to a big car. And you all need these three information: localization and the distance and what are around you. So for the company I founded is more on the what is around you. But for the other two, I think there are a lot of other opportunities to do. Okay, so these are what I'm doing in why I'm doing for the deep learning, because we are looking into the surveillance. So surveillance is very important, and we have money to get back to the company. And the second one is the robotics, not only the drones, but also the automotive part. And the third one is the server part. So I think these three are the application domains that have some money. But if you want to do the key algorithm in these three areas, then you need to know about the neural nets. So when I look into the neural nets, firstly I try to analyze what is more important for the different layers of the neural nets. So we can see that for previously, this figure is drawn in 2014 or 15. So we can see that for the computation part, these 5 neural nets are grouped into, all of them have 5 big count layers and 3 big fully connected layers. This is fully connected, this is convolution. So 5 convolution layers and 3, so these are the convolution layers, and these are the fully connected layers. It's quite clear to see that for the count layers, they are all computations, because you are trying to compute the small kernels to go around your feature map or go around your original figures. So they are all computations, right, to do the multiplication and addition. So we calculate and find out that, hey, this is true. So the count layers are bounded by computations. And for the fully connected layer, they are bounded by memory access. I would say that because for the weights, because you need some the input and the weights of your neural nets, you can try to do a statistics analysis. You can see that for the first 5 layers, the weight is quite small. The volume of the weight are quite small. But for the last 3 layers, especially for the first FC layer, fully connected layer, you have a lot of weights. That's why, because this is a huge matrix, vector and matrix multiplication. So for this big matrix, about several thousand by several thousand, then you have millions of weights. So these are why the weight is very high. And for these, each of the weights in this big matrix, you will use it for only once. So the moving the data onto the chip or into the chip and calculate only once and drop it away. So these fully connected layers are bounded by memory access, not the computation part. So they are quite different from the COM layers and the FC layers. So for the first time, I'm doing the accelerator before I move into this deep learning area. So I just say, hey, then I just design an accelerator for convolution part, and then I design an accelerator for the fully connected part, because they are quite different, right? So this is the initial thinking of my thing. So, but for this figure here, I just trying to show it is quite amazing when you put a image into this neural nets, and you need to go through about 30 gigaops, and then you can have your result. So it's quite complex. And so, and these are, I think I will go through it quickly. So this is the CPU and the scaling down the CPU part. And then we can use, how we can use this CPU for such large models. Then we can see that, okay, these are the, for the MNIST, this is a very small data set, right? All right. So you use the CPU to do the training, and then you can, and at 2006, you have this kind of very deep neural nets and published in Science, and then you have this large convolution neural net. Sorry, I didn't translate into English. So you have a very good accuracy. So this is a very small task. And then if you want to get a bigger task, then you need to XPU. Then this comes into the way is the GPU part. So you can see for 2010 and 2010, then you use the computer vision algorithm, traditional algorithm to do this, and the error rate is around 25%. So this error rate on the ImageNet. So then 2012, you use multiple CPU, and then you use GPU, and this 2013 is GPU, and here you use a CPU cluster, and then 2015, everybody used a GPU cluster to do the training part. So the question is GPU enough? So taking the consideration of what we are thinking about as robotics and cloud service and ADAS and smartphone, from the embedded part and to the cloud service, and we can see there are some of the applications that need low power, low latency, and high throughput. So you need this kind of different or more energy efficiency for this GPU part, because GPU is very good for the training. If you know more about the algorithm, then you know that for neural nets, if you have an input image, then you have an output. And if you have this weights inside the neural nets already there, you have a trained neural nets. And if you do only once, then we call it inference, right? So this, you may need low power, low latency, and high throughput. But if you're trying to do the training back and forth, because you do have an initial input and then you have an output, and you compare with your very good result, and you have the data, and then go back to, that is the BP algorithm, so you can try to look into the textbook to find the BP algorithm, and you do the back and forth. And if you want to do this kind of back and forth, then most of your computation is the matrix operation. And especially it is dense. What is the dense here? That means if you look at the matrix, almost all the elements in this matrix are non-zeros. So, and GPU, if you know the internal architecture of the GPU is very good for the dense matrix multiplication computation, because when you design a GPU, or the GPU is designed for the graphics, right? So for this kind of, you have all these pixels here. So actually, previously you need to do for this each pixel you do a task, and these tasks are almost the same. So you have the CMD, same single instruction multiple data for this dense matrix. So GPU is designed for this dense matrix multiplication. So then it's quite good for the training part, because training, we all have this kind of dense matrix operations. especially for the data computation and the update and or dense matrix. So GPU is more powerful for the training part. Why we are doing this inference part? Because we are thinking about that this dense matrix assumption may not be true. This is what we are trying to do is we're trying to turn the, or we feel or we foresee this kind of deep learning structure to be a sparse one. So this is the key idea of this what we are doing on the FPGA or the chips, because we believe for the inference part it is sparse, not a dense matrix multiplication. So then we do the rest of things. But so here is actually I'm just trying to explain what do we choose here. So we have CPU here is high flexibility but low efficiency, and we have the GPU here is a high performance but it's also high power and rely on the batch because it's a dense matrix multiplication. So you need to group all the input into a big matrix, and you have this kind of dense matrix to be efficiently run on the GPU. And also here is the other two options. Well, I didn't list the DSP here because the DSP is kind of similar to this part because it's a carefully designed data digital signal processing engine. It also can be included in the ASIC. So a lot of DSP designers are trying to fit their designs into or match the deep learning patterns. So the other two choices are FPGA and ASIC. So firstly, we choose FPGA. There are a few reasons we choose FPGA. The first one is flexible because the algorithm is still evolving. Algorithm is changing, right? So this is the very first one. If the algorithm is changing, so you cannot design a fixed accelerator on the chip or using ASIC to do that. So the algorithm is developing. The second one, you have a quite good time to market. So if you design an accelerator on the FPGA, you may only need about 3 to 6 months if you are an experienced engineer. And the third part is the power and the performance. It's quite good. For power is ranging from 2 watts to about 100 watts. So it's below 100 watts. So power is quite good. And performance is, we are trying to use the FPGA to beat the GPU part. So for the inference. So I think performance is also very good. So I will show the numbers later. So this is for FPGA. And if we are trying to converge the architecture on the FPGA, if the arc is converged, then we can try to move it onto the ASIC. So this is what we are trying to do is firstly on the FPGA, and we have low power programmable hardware, but the performance is average or comparable to the GPU or other DSPs. But if we change this one into the ASIC, then you can have even lower power, higher performance. But the drawback is you have low flexibility after tape-out. So you need to think carefully about that architecture and to support more neural nets, or you support your dedicated application very well. Also, there are some numbers. These are the why I'm I'm doing the hardware acceleration because when I graduated from the university, I was in a platform device group, which is a hardware group, and we designed the key algorithm in the search, and we have the power of the 1% of the power of the clusters, and the energy efficiency boost for 1,000 times. And 2010, the Microsoft research in Redmond, they announced that they are researching or putting FPGA in their infrastructure systems. And then in 2014, they have the ISCA paper saying that, hey, we have 400 things, and then we have the put a few, several, dozens of thousands of the FPGA into the data center. And in this year, they are trying to say, hey, we are designing the AI chips. And also, one of the other very good example is the AlphaGo here. So they have the very big system at the beginning, and then they have the 50 CPU distributed here for the Shishi. And then you have the CPU in a single box. So this power reduces about to 1000x. Even if they have very good improvement on the algorithm, but these power breakdown is also benefit from the TPU design. So it's quite amazing. So all these are quite big trend of the deep learning part. So when we are trying to do this work, we go back to read all the papers of the computer deep learning related work. So we can see that before 2014, there are only two very good papers. One is in 2010 and one is in 2012. And this is, I think it's from the, I don't remember the name, but this is a very good algorithm guide to do this for work. And this is from the NEC. And this is from Chinese Academy of Science and Dianao series. So this is the first one of the Dianao series. And this is the CVPR workshop, and also from this guy, I think. So for 2015, also two papers. One is Dianao series, and the other one is the first FPGA work by Jason Hong, and using high-level synthesis and to do the FPGA-based accelerator design for the DNN. For 2016, there are more important papers, we think, and we listed here: ICC1, ISCA, Micron, DAC, FPGA, FPT, FPGA, FPL, and ISOPD, and ISCA. All these are the papers that I think if you want to go into this area, then you need to read. And for 2017, there are even more papers, and now we are not at the end of the 2017, so we only list the one we find out for now. So also ICC, more ICC paper, HPCA, TBSI, TCAT, DAC, FPGA, FCCM, and FCCM paper. And also ICC, FPGA. So this is our FPGA-based paper, and the ICC, and also archive, because actually this is this should be a ISCA, because this is from the Tensor TPU, and this is ISCA. So we can group all these papers into two parts. One is to improve performance, not only the speed or the energy efficiency. And the other one is design automation, how to design this kind of accelerator more efficiently. So we try to have a map on my website. So if you are interested, you can go to this website and to see what are they. So you can see that these are the best. So this is the power. So this is the power. So this is power. Why I'm doing power? And because we are doing the energy efficiency, high energy efficiency. And this is the performance. So for embedded device or IoT device, you may use this kind of power range. And if you are trying to look into the cell phone, you may need to look at the 0.5 watt accelerators. And if you are looking at the edge, and it may be 1 to 5. And if you're looking at the data center, then you may need to look at the 10 or more. 10 watts or more. But interestingly, you can see less than 10 watts. You don't have a peak performance over very few. This is a simulation part. So you can see that the green one is testing result. The pink one is simulation result. So for testing results, a few of them is existing. One, this is a 1K, so it's a 1 tera ops, the performance, 1 tera ops. So this is the one thing. And the other one is, this is the TPU. This is the TPU, and this is the most, I think is the best result for now. Best result for now. So if you are playing with this, or I'll try to play with this in the middle of the class, and you can see that you can choose the year, and you can see the year in 2015 and 2014 only 2, and 2015 only 2, and the other one. So you can also only choose FPGA or ASIC, or we are also putting the RM into this map. So it will be quite useful. Then if you click on each of the points, then you can find the bit or the information of each paper. So talking about to improve the performance. So reading all these papers, we are thinking about you need to improve the whole system performance. So to improve the performance, we think there are 3 very important things. One is to lower the workload you are doing. So this is the thing that you may need to do with the software. And the second one is you need to boost the peak performance. You need to boost the peak performance, and you need to boost the efficiency of this peak performance. Because if you put so many cores into the chip, then if you're doing a task, only a small portion of the cores are running, and the efficiency is low. So for deep learning, a very important thing is the model design. So we are not the expert of the model design, so we put it here. This will greatly influence the performance of your system. We are not the expert, so we put it here. What we can control is the other part. So if we have a model, and you have already trained a model here, and then you can do the compression. What is a compression? More is it means that you cut the internal weights and turn it into 0, or cut the neurons, and you have a smaller net. So you will have smaller workloads. But the basic constraint is you cannot downgrade the accuracy. The second one is quantization. So if you are using an 8-bit or even less bit for the weights, data, and other things, then you can put more hardware or more computing units in the hardware. So you will boost the performance. Thinking about the 32-bit multiplier and the 8-bit multiplier, the resource you use may be very different, maybe 10x. So quantization is very important. And the other one is the hardware design. You're trying to boost the peak performance, and hardware design is closely interaction with the mapping part of the efficiency. So this figure is what we are thinking is very important. So you need to do something in the software level, and you need to do something in the architecture level, and also at the circuit level, we can do some tricks to to improve the performance. So let's see some examples. We quickly go through the examples. The first one is software optimization. This is the reduce the bitwidth. So you can use the linear quantization of 16 or 8-bit fixed point format. Actually, we do it in our first FPGA paper in 2016, and we can use 8-bit for all the computations, including the convolution and the fully connected part. And also you can use the nonlinear quantization because the weight, this is the weight distribution. So you can see the weight distribution, you group into two very high, very dense part. So then you can use a nonlinear quantization to quantize all these data. And then you have your representation of the nonlinear quantization. So the second one of the software optimization, you try to reduce the model size. Reduce the model size, then one way is use the mathematic method. Then you use the low-rank approximation, such as the SVD or 1D convolution approach or PCA. The basic idea is changing a large matrix operation to several small matrix operations, and they are the same from the, or approximately the same from the mathematical view, but they will have less computation or the storage requirement. So this is a low-rank approximation. And the other one is empirical way, because you are training the neural nets. So you are doing the training, and within your training, then you can do the pruning on the network neurons, such as you can prune some of the neurons and some of the connections of these. So you will have less weights and less neurons of the neural nets. But this is inside the training part. At the training part, when you see a connection is very close to zero, you can fix it to zero, and you never change it. So you give a rule that you are not changing this weight. You fix it to zero, then you can train using other ways to compensate the degrees of this fixed to zero accuracy decrease. So then you can have a neural net model with similar accuracy. So we can see that for different model size, then you can boost to the accuracy loss. You can boost also to the zero, so almost zero. But for if you model size ratio of compression is too low, then you still have the accuracy loss. And fast convolution is also a software optimization from our perspective. So you can use FFT and Winograd. That means if you treat the convolution of the go through a picture as a matrix operation, then you can use this kind of this is a Winograd operation, and you can reduce the multiplication from 36 to 16. But you will have a drawback, because when you are doing the quantization, if you're doing the quantization, you can have 8 bits for each operation if you don't use the Winograd. But if you're using the Winograd, you need more precise calculation, and you need 16 bits for the calculation. So these are all the trade-offs. So we list each of these techniques here, but combining with these techniques, we'll have some conflicts. So from the architecture level design, actually for convolution part, especially for convolution part, it is 6 loops of, especially they are written as a nested 6 loops. One is output channel, and the feature map is a 2-dimension, and the input channel and count kernel as 2-dimension. So these are 6 loops. So basically, you can think about this is a you can have this kind of workload as split into n steps, and then you put each steps into the hardware and go through the n steps, and you have all the computation done. So this is the basic concept. But treating these 6 loops, we can have some loop unrolling, loop interchange, loop timing. So it basically is a queue of, because it's a queue, and then you can put only part of it onto the hardware. So you can put only part of it on the hardware. So loop unrolling is a spatial mapping of these and decide hardware size in each parallel dimension, because you have six, maybe six, but you cannot utilize 4 of them, and that affects the peak performance and the utilization ratio. That means for this loop unrolling, you are designing the shape of this cube, small cube, working on the hardware. And then the loop interchange is a temporal mapping. Then you go this way, or this way, or this way. So this is the loop interchange. So it decides how to use the data and decides the on-chip memory design and affects the off-chip memory access. And loop timing is decides the data block size. And each computing task. This is often combining with how many on-chip memory you have and how many off-chip memory you have and what kind of the memory, and you do the loop timing and do the scheduling here. So we're trying to look back into these. Okay, so these are too small. Right? You can read all this one. Yeah. This is the first work of the FPGA 2015. They choose the unrolling strategy. It's a very simple one, and when they fix the loop unrolling strategy, then you can try to print all the possible solutions on the root-line model and trade off between the performance and the computation to the communication ratio. So this is a very important metric for the CNN. And the second paper is the FPGA 2017. So they have a more detailed analysis based on the previous work. And they choose the interchange and timing strategy to minimize external memory access. So we'll talk about the external memory access. Actually, the moving a data is more energy consuming compared with the computation inside this neural net computation. And there are also other unrolling designs, so such as the kernel loop, because there are 6 loops, so you can choose several loops to do the unrolling. And so if you choose the unrolling the convolutional kernel loop, and you can fully reuse the data with a feature map and the convolutional kernel, but it's hard to adjust the different kernel sizes and strats. That means if you design a 3x3 kernel, then the line buffer size is 3 lines, and you just pick these 9 elements out, and this is the weight buffer, and this is also 9, right? And you do the 9 multiplication and add it together. So this is fixed. But in the convolutional neural nets, there is not only the 3x3, but when we do this work back to 2015, we find out that 3x3 is a large portion of the kernel, so we just choose this fixed design. But if you want to do a 5x5, then you need to use this kind of 3x3 to put it together and to calculate the 5x5. Or if you want to calculate only 1x1, then you will have a large resource waste. And also, this is 视电脑. This is from ISCA 2015. It's unrolling the feature map and the pixel loop. It is more fine-grained design, so you will reuse the data within a feature map. It's flexible to different convolution kernels and size and stride, but it requires a very complex data bus to design how to put the data into all these 9 PEs. And also, this is I think on Friday, the Aries author will try to explain more, but this will be category into configurable unrolling parameters. It can maximize the T utilization ratio within a P array, and it's quite flexible to different kernel sizes and strengths. So I think this work and this one is quite good to flexible to different computing kernel sizes and strengths. And you may pay more attention on these two papers. And besides unrolling, because unrolling is more in a one layer, they also have multiple layer designs. Why we need multiple layer designs? Because when you calculate one layer, you do the convolution and you generate a feature map. And if you're doing only layer by layer, then you need to put all this intermediate data onto the object memory, and this will consume a lot of power. For this multiple layer design, they're trying to reuse these data, and you put the data on the chip for a longer time. That means you put the feature map here because this feature map will be the input of the next layer computation. So then they trying to align this kind of reuse strategy. They use some of the feature maps for the next layer computation, and then reduce the object memory movement of this kind of intermediate feature maps. This work is in 2016 micro paper. So they map all the layers, but at that time they map all the layers onto the hardware. But this is actually not feasible for every time. Merge layer as groups and map each of the group onto the hardware. So this is the IPR paper. This is the micro paper. So if they put several layers on chip, then they can reduce the external memory access. But it needs large on-chip memory. So you can see that different methods have different drawbacks. If you have larger on-chip memory of your platform, then you can try this kind of method. Another architecture level design is to utilize the sparsity. That means because you want to do every computation efficiently, so you need to squeeze all the zeros out. So this kind is putting the skip the zero weights at runtime on the hardware. So what we are doing is trying to pruning. Pruning then is you have a sparse neural nets and then design a different architecture for the sparse matrix multiplication. For this one, you're trying to group different subunits. This is actually the 大电脑 paper, and the ISCA 2016 paper, they changed the 大电脑's architecture into this kind of sub-unit, and in each sub-unit, they can skip the zero weights at a long time. So this is also one of the methods to skip all the zeros and boost the efficiency of the neural net computation. So these are for the architecture level decisions, and you need to make when you have your targeting platform or targeting neural nets. And the other one is the circuit level design. Actually, this one I also think is architecture level thing. Because for the TPU, actually this is the systolic array, right? Systolic array is in the TPU. TPU is, they have a large P array, right? And then they have the input from only this way and into the, putting the data in it, and you go in a fixed way and go to the output. So when you look at the TPU paper, then you need to reorganize the data. So this is one of the drawbacks. And the other one is, but the merits or the advantage is also very important. They have only n input from the memory. So it's a scalable design, right? So if you have n by n a PE here, and if you have another design which have each PE directly access to the SRAM, then you will have n by n process or routines to feed the data. But for this historical array, you only have n. Right? So if you turn the P from 10 by 10 to 100 by 100 or 1000 by 1000, you only have the linear increase of the memory access. But if you have this each PE directly go to the memory, then you have n by n memory channels you need to provide the data. So this is, I think, why TPU is more feasible for the big designs, because they don't have that complex memory access patterns. So they reduce the routing cost with the cellular array. And also, you can use this kind of circuit level design, because such as you're trying to detect the zeros. If you detect the zeros, then you keep the input of the multiplier fixed. Then you do not lead to the flip of this multiplier. So you will not have the net power of this multiplier. This is also in the ICC paper Iris. So it's a very clever design. So you detect the zero and you fix the input of the multiplier, and then you can reduce the power of this multiplication step. So you will save about 45% of the energy. So you can see a lot of zeros in this neural net computation. And also you can not only have this fixed data bit width, or you can also have this dynamic adjust the data bit width, such as you can have 16 to 8 bit or 8 by 8. Normally you calculate it from 8 by 8. That means you have 8-bit and 8-bit multiplication. If you overflow, then you go back to the you detect overflow, then you go back to 16-bit. And you can have the accurate results and do it in the circuit level. So it will be much more safer. So this is a very clever design. And also the traditional DVFS, dynamic voltage and frequency scaling, is also very important, because for neural nets you have some kind of error resilience inside. So you can lower the power or lower the speed when you want to lower power. So you can lower the VDD or the frequency of your design. And another one is the multi-level on-chip RAM design to optimize the energy of frequently accessed data. This can be done. This can be done only because this deep learning is kind of a fixed architecture, and everything or every data movement you can predict before you do the calculation. So because every application of this inference part can be read into a DAG, right? So I assume everybody here is 有项无关图 DAG here. So this DAG is fixed. So if you have this kind of fixed DAG, then you can predict each memory access beforehand, and then you can design the multiple level of the memory hierarchy. So this is one thing. And also they also have some, because this is, I think, this year ICC paper, they design a TSRAM allows both row and column access to increase the bandwidth or increase the flexibility of the SRAM design to lower the power. So, and this is also go back to the figure, and we can see that this is a 1 teraops per watt, and most of the designs is 1 teraops per watt, and especially for this lower part, you have higher energy efficiency. But to be careful, these designs, they don't have off-chip memory access, so they don't include the DRAM part inside. If they don't include this DRAM side, then they will eliminate a lot of power, a large portion of the power. So for this part, or for the FPGA design, most of them have the DRAM part, so they have they are lower than 1 teraops. So this one have a very large. This is TPU, but this one have very large on-chip SRAM. So they try to eliminate most of the off-chip memory access, so they can boost to 1 teraops per watt. So if you want to go to 10 teraops per watt, then you may need to put everything on chip, at least for nowadays design. Yeah. But human being, I just try to put another goal here. That is 500 teraops per watt estimated by IBM in the match. They try to have the total energy of their Waston, and then we can see that there is at least a 50x if we try to see this one as the state of art. So what we can do, how to fill the gap. So in this 10 teraops per watt design, that is this point, right? I just in the last figure, they have integrated the DNVFS and 4-bit data and computation and data compression and systematic array. A lot of techniques have been already put into this design, but we still have techniques to use, such as improve the technology node, right? So you can use a more advanced technology node, then you can have 2 to 4x energy efficiency boosting, and you can try to use the sparsity because we can see the zeros may have about 50% of the energy consumption, so you may have this sparsity. And you can also try to use fast algorithms, such as a fast convolution part, and you also have about 2 to 3x. But these integrate together is about 8, right? It's an 8x. So it still have quite a far gap. So what we can do? So maybe an computation, RM, or software revolution. So I think this part may be more feasible. Okay, so quickly go through the design automation part. So design automation part, we have apparently two things. One is the using the basic parameterized the function modules. That means if you have the model, then you have the DFG, the data flow graph. So that means you have this one. And then you have some constraint of your platform. And then you can switch into computation steps. And you have the basic function units here. And you integrate together and you change it into RTL. But because this one is RTL here. So you put it into RTL and you put it onto the hardware. So this is a Micron 2016 and the DAC 2016. They all use a similar method to do the RTL level design automation. And the other one is what we are trying to do is trying to do the instruction level design. So that means you extract the common operations in the neural nets and compile a neural net model as a set of instructions, And you change a neural net here, a DAG here, different DAGs into different instruction series. So for the Kentrican, that is from CAS, China, they have this kind of instructions. And Google TPU has this kind of instructions. And in each of this is a basic operation. But for us, we have also different instructions. So this will be what we are doing for now. So we have about, sorry, we only have 2 minutes. So any questions for the first slot? Okay, so this is a very good question. Actually, people, when I go back to the figure I draw, on the website, actually NVIDIA's, they send me email. The NVIDIA engineer sent me email. Hey, why you put GPU here and TPU here? It's much better than GPU. So then I told him, hey, this is the real performance. I mean, what is the real performance is the performance we put a AXNet or VGG here and run a single batch, and we get a speed, and we get a power, and we get put the dot here, right? So this is the real performance. But for this one, TPU, we can only grab the data from the article. So they have the peak performance. So for this figure, we use the peak performance of the peak performance and the PDB of this calculate this dot. But still, we can only use the existing numbers from the VGG, AXNet, ResNet, or this kind of what they call most commonly used nets to do this kind of evaluation. And each paper, most of them evaluate the VGG and AXNet maybe, but very few of them evaluate ResNet or the more emerging or the more recent nets because they are more random, or the structure of that kind of net varies a lot. So maybe their work cannot support this kind of, or they need more time to port the ResNet or the quite different nets onto their hardware. So for now, we are also discussing with some researchers and trying to have this kind of a benchmark set. So if you have a benchmark set of different nets, and such as you have ResNet, or even ResNet, you have 14, 50, and 101, or 1,000 layers. So they have different kind of ResNet, so to test, or they have then we can have a benchmark, we can have an average, such as average performance of your hardware. So that would be, I think, more visible for comparison. Yeah. So this is. From our perspective, yes, because moving the data from the DDR into the computation part, or the near to the computation, such as multiplication or addition, is consume more power than computation itself. So eliminating the movement will be more important. So when you're designing your hardware for this kind of neural net acceleration, eliminating memory or object memory movement will be more important. Yeah. For time part, I didn't have the exact numbers. Yeah. But you can try to calculate in this way. If you have a full utilization of the bandwidth, and you have the volume of the data you need to move, and you can calculate that. So especially roughly estimate.